This problem is the same as in the previous video. Y double prime plus 2y prime minus 3y equals to 5 sine 2x. And we've already established the complementary solution. We're going to approach it differently by using complex numbers. And here's how we'll go. Now this is an alternative method of working it. I'm not so sure it's more efficient. It's probably roughly the same. But it's a wonderful illustration of using Euler's formula to in a productive way. So here's what I'm going to do. Instead of solving this equation, I'm going to solve this problem here. It'll be y double prime plus 2y prime minus 3y equals to 5 e to the 2ix. Alright, now remember that the e to the 2ix is going to be cosine 2x plus 5i. Whoops, let's try that again. Cosine of 2x plus I times the sine of 2x. So if I multiply it by 5, I just have 5 sitting here. So if you look at this, 5 sine 2x is literally I times 5 sine 2x. And in fact, the imaginary part of this complex number is 5 sine 2x. So when I solve this problem, if I look at the imaginary part of the solution, I should get the answer to this problem up here. That's the idea. So we'll get started. I'm going to let my y particular, since I have an exponent form here, let's let y particular be a e to the 2ix. And now it's interesting here because I only have one unknown, but there'll end up being two unknowns later on down the road. So we'll see that happen here in a moment. So the first derivative is going to be, the derivative of e to the 2ix is going to be e to the 2ix times the derivative of the coefficient. So the derivative of the coefficient is 2i. So I have 2i a e to the 2ix. And then the second derivative will be same idea. We'll end up multiplying by 2i. I have 4i squared a e to the 2ix. And I squared, remember, is negative 1. So this becomes 4 times negative 1 minus 4 a e to the 2ix, which is minus 4 times the function y, minus 4 y particular. So that part we saw earlier with the sines and cosines method. So now then, when I plug all this stuff into here, I've got minus 4 y particular. Let me write that correctly. So y double prime, I'm going to rewrite as minus 4 times y particular plus 2 y particular prime minus 3 y particular, and that equals to minus 7 y particular plus 2 y particular prime. So that should look familiar from the last example. And then when we plug into here, I've got minus 7 times y particular, so that's minus 7a e to the 2ix, then plus 2y particular prime, so that's plus 2 times 2i, 4i, plus 4i a e to the 2ix. And that equals to, let me write it up here, so I'm going to jump up to here. When I combine these, I'll pull out the a e to the 2ix, and I have minus 7 plus 4. Minus 7 plus 4i, rather. Minus 7 plus 4i, a e to the 2ix. Okay, now that is supposed to equal to 5. e to the 2ix. So let me do a little erasing here. So as I was saying, what we got when we plugged y particular into our differential equation, we ended up with this expression here, minus 7 plus 4i, parentheses a e to the 2ix, was the left-hand side. The right-hand side was 5 times e to the 2ix. So if I just divide both sides by the exponential part, e to the 2ix, I have minus 7 plus 4i a, parentheses a, equals to 5. So I'm going to erase some of the clutter here, and then we'll wrap up this problem. So our method of undetermined coefficients by using complex numbers boiled down to this. I have this complex number, minus 7 plus 4i times a equals to 5, which means that a is equal to 5 divided by minus 7 plus 4i. Wow, so what do we do with that? Well, I'm going to rationalize the denominator, and the way to do that is to multiply top and bottom by the conjugate of the denominator. In other words, I'm going to multiply top and bottom by minus 7 minus 4i. Minus 7 minus 4i. Okay, so the conjugate is the same binomial term except the middle sign is changed. That produces a difference of two squares, which is going to eliminate the I from the denominator. So that's really what we're trying to do, is to eliminate the I from the denominator. And that's going to make this simpler to deal with. Alright, so let's multiply this through here. I've got 5, for the moment I'm going to keep it factored. 5 parentheses negative 7 minus 4i divided by, down here I've got positive 49, positive 28i, minus 28i, those two cancel, and then minus 16i squared. By the way, I teach this part right here in college algebra, so it's possible you've seen division of complex numbers before. Well, here's where you might use it. So we got 49 and then minus 16i squared. Well, what's minus 16i squared? That's plus positive 16, because I squared is negative 1, and 49 plus 16 is 65. So we end up with, and I'm going to factor the negative out, minus 5 parentheses 7 plus 4i over 65. So if you remember the solution from the last video, it's probably starting to look kind of familiar here because we have 65s and 7s and 4s. Now then, what are we going to do with that? Well, that means my particular solution is a, this number, times e to the 2ix. And what I want to do, let me write that in, minus, oh, I'm sorry, the 5 and 65 cancel, leaving a 13, so that's even better news. So let's write it as minus 7 minus 4i, minus 7 minus 4i over 13, parentheses e to the 2ix. Alright, so we took a, we simplified it best we could, and here it is, and then it's a times e to the 2ix. Now, let me erase this and we'll try to finish up. Now you may recall at the beginning of this video that I said that the solution to this problem will be the imaginary part of this solution. Well, what does that mean? So I still have this mix of complex numbers. So at this point, I'm going to factor out minus 1/13. Minus 1/13, parentheses 7 plus 4i. And then I'm going to rewrite e to the 2ix in sine and cosine form. So that's cosine 2x plus I sine 2x. And that's how we end up with sine and cosine for our answer. By converting this to sine and cosine form, I'm now going to multiply all this mess out. So it's minus 1/13. And we're going to have 7 cosine 2x, and then we'll have 7I sine 2x plus 4I cosine 2x. And then the last one is going to be 4I squared. Well, 4I squared is minus 4. Minus 4 sine 2x. So I'm going to reorganize this a little bit. Minus 1/13 bracket. I'm going to put the real parts together. The 7 cosine 2x minus 4 sine 2x. And then factor out I, and I'll put the imaginary part together, which is 7 sine 2x plus 4 cosine 2x. So again, this is called the real part because it doesn't have the I in it. This part over here is called the imaginary part. And we had decided at the beginning of the problem that the solution to this equation is going to be the imaginary part of this solution. So let's do a little racing one more time, and I'll write out the full answer. And so here's our general solution. Y is c1 e to the x plus c2 e to the negative 3x. That's our complementary. And then our particular solution was the imaginary part of this solution. So it's minus 1/13 times, and I reorganize this, 4 cosine 2x plus 7 sine 2x. I looked it up. That's the same solution we got in the last video by using a different method. So there you go. You might say that we solved 2 problems at once here. We actually solved this problem. We also solved, in essence, 5 times the cosine of 2x. And that solution would have used the real part instead, if this had been a cosine 2x. Not that one would need to solve both, but just an observation there. So there you go. It's an alternative method using complex numbers, which I find pretty fascinating. So I thought it was worthwhile showing you this alternative method.